In question 3 on the test, we have a conductor with an irregularly shaped cavity. So the white space here is the cavity. The gray part is the conductor. There's a point charge of plus Q inside the cavity. The net electric flux through the Gaussian surface shown with a dashed line, that's this circle right here, or the sphere, is flux equals minus 2Q over epsilon naught. Notice here, this Q is the same size as the Q of our point charge. Okay, so that's how the flux is related. Find the net charge on the conductor. So let's think about what's going on with this Gaussian surface first. The net electric flux through that Gaussian surface is given as minus 2Q over epsilon naught. The other thing we know is from Gauss's law, the net flux is the charge enclosed by the Gaussian surface divided by epsilon naught. Okay, there's one bit of information. This tells us, by comparison, that the charge enclosed by this Gaussian surface is equal to minus 2Q. Okay, there's one bit we know. The other thing we know is that the charge enclosed by this Gaussian surface is whatever charge is on the conductor plus our point charge. So Q of the conductor, so Q con is this charge right here, plus our point charge Q. Let's put these two ideas together. Minus 2Q equals Q of the conductor plus our point charge that's in the cavity Q. Let's solve for Q of the conductor equals minus 2Q minus Q equals minus 3Q. So that's the net amount of charge on our conductor. Next, we want to find the charge induced on the surface of the cavity. What we know about conductors in electrostatic equilibrium is whatever the charge is, it's distributed over the inner surface. We'll call that amount of charge Qi for Q inner, and the outer surface. We'll call that Qo for Q outer. So whatever this charge is, it's split up over the inner surface and the outer surface. We can figure out what those are. For part B, what we'd like to do is find the charge on the inner surface. What is Qi? Let's draw a Gaussian surface inside the conductor. So for any Gaussian surface, maybe I'll say for the Gaussian surface, the one I just drew, in the conductor, the thing we know is that the electric field is equal to 0. Because that's because our conductor is in electrostatic equilibrium. Let's write down Gauss's law. The net electric flux through the Gaussian surface that I just drew is the integral of the electric field over the area. Got to write this integral form because I think the electric field or the area of this surface is hard to figure out. But at any rate, because the electric field is 0, this whole thing is equal to 0. Equals Q enclosed divided by epsilon naught. This tells us that our Q enclosed is 0 times epsilon naught, and Q enclosed must be equal to 0. So the net charge inside this Gaussian surface has got to be 0. Okay, the other thing we know about Q enclosed is what's ever inside this dotted line. So the only things with charge inside this dotted line is the inner surface Qi and the point charge. So that's my second thing I can write down. Let's put in my 0 here for Q enclosed. So Q on the inner surface is negative Q. This makes sense physically because negative charge is attracted to this inner surface because it's attracted to this positive charge. So the negative charges are drawn to that positive charge. Part C, find the net charge on the outer surface of the conductor. Well, what we know about the total charge on the conductor is that it's equal to negative 3Q. And we also know that the total charge is split over these two surfaces. So the Q on the conductor is Q on the inner surface plus Q on the outer surface. Let's put all this stuff together. Minus 3Q is Q of the inner surface, that's minus Q, plus Q of the outer surface. Q of the outer surface is minus 3Q minus minus Q equals minus 2Q. So there's question 3 for me.